In today's lab, we're going to measure Planck's constant, which is a fundamental constant relating to light, and we're going to measure this using some LEDs and a spectroscope. Before we do that, I need to briefly explain how an LED produces light. So when you apply a voltage across an LED, it causes the electrons to flow. It removes electrons from the material and then causes them to flow freely. Then when the electron recombines with the material, it loses energy and a photon of light is emitted. The energy of the photon is equal to the energy lost by the electron, and the energy of the electron can be determined from the voltage necessary to remove it from the material in the first place. In equation form, the energy of the photon is equal to hf, and the energy of the electron is equal to E times the absolute value of V naught. Since these are equivalent, we can say that hf is equal to E absolute value V naught, where h is Planck's constant, f is the frequency of light, or the frequency of the photons, E is the charge of an electron, and V naught is the voltage necessary to remove an electron from the material. Then with this equation, if we measure voltage, V naught, and frequency, f, we can determine Planck's constant, h. Now let me introduce you to the spectroscope. So this is an optical tool that allows you to see the spectrum of colors in any light source that you pointed at. When you look at it, you should see three different openings. Here we have the eyepiece. This is where you look into it. And then on this side we have the slit. This is where the light comes in. And then this long slot here is the wavelength scale. So on the other side of that is a printed scale with markings indicating the wavelengths of light that are entering this slit. When you look through it, hold it up to your eye and orient it so that the wavelength scale is on the right side. If you have it the other way around, then the numbers will be upside down, but you'll see that when you look through it. So right now, this is looking through the spectroscope at my desk lamp, which has a CFL bulb on it. And you can see we've got very specific bands of colors representing the frequencies in the spectrum of light produced by that light bulb. On the right side there, you can see the wavelength scale with the numbers 4, 5, 6, and 7 on it. So those represent hundreds of nanometers. That would be 400 nanometers, 500 nanometers, 600, and 700 nanometers. And then in between those, we have 10 lines. So each of those lines represent 10 nanometers. So say that blue line there, that one looks like around 490 nanometers, or maybe just a little higher, perhaps 495. And then the green one next to it, that one looks like maybe 540 or 545 maybe. So you can just see where the colors line up and then read the wavelength from the scale. Now there is one problem with this. The slit on the spectroscope is very wide, which means the color bands are also going to be very wide, and this makes it difficult to read a precise value for the wavelength. This isn't too much of an issue for a light source like my CFL bulb, which produces very tight bands of color, but for the experiment, the LEDs are going to produce a much wider smear of light, and so in order to reduce the width of that smear and read an accurate value for the wavelength, we need to reduce the width of the slit. And we're going to do that with some electrical tape. So try to get this pretty narrow. The trade-off is that the narrower you go, the dimmer the light will be. So you'll have to find a balance between accuracy and the brightness of the light. Then use another piece of tape to cover up the bottom half of the slit, and this will shorten the color bands and make them stay close to the wavelength scale instead of spreading out all the way down to the bottom. I think I've narrowed the slit down to 0.5 millimeter or so. And I'm just going to look through this and make sure that it worked. So yeah, I think that looks pretty good. You may need to adjust yours after you've looked through it if you're not happy with it, but for mine, I think this is going to work just fine. Before we go on to the next part, I want you to find some different types of light sources and look at them through the spectroscope so you can practice using it. And I shouldn't need to say this, but please don't look at a laser or at the sun. Just like looking at those normally, it will damage your eyes, so please don't do it. Anyway, I'm going to go find some different light sources around my house and look at them through my spectroscope, and I want you to do the same with yours. Here we have a regular tungsten light bulb, and you can see that the colors are much more spread out, almost like a rainbow, instead of the distinct colors like we had from the CFL bulb. Here in my garage, I've got a fluorescent light fixture, and you can see it's got a pretty wide spectrum of colors, although it does have a couple distinct color bands in the middle of that. So it's got one at blue, green, orange, and red. Now we need to build our circuit to control the LEDs, and this is actually the same circuit that we used in the inverse square law experiment. So if you built it for that, then you should already be familiar with it. But either way, I'm going to build it again for this lab. Let's start by finding the resistor that we need. So we're going to use a 470 ohm resistor. And we won't need to measure it because we're only using it to limit the current flowing through our LED, but we do need to make sure that it is the 470 ohm resistor so that it limits the current the right amount. I've already explained in previous videos that we can identify the resistor from the color code printed on it. So a 470 ohm resistor with 4 color bands is yellow, purple, brown, and then the tolerance. And the tolerance in my case is gold, plus or minus 5%. So again, that is yellow, purple, brown, and then gold. But if you have a different number of color bands on your resistor, then you will need to look it up in that number of bands. Now I'm just going to build the circuit real quick, and then I'll explain after I've done that. Alright, this is the circuit, and I'm going to walk you through it going left to right. So on the left here we have the battery, and the red positive battery wire is plugged into the red positive power rail on the breadboard, and then the black negative battery wire is plugged into the blue negative power rail on the breadboard. Then over here we have the potentiometer, and you can see that we've got jumper wires on either side of it. To make this easier, I'm going to remove it for now, and then I'll explain what these jumper wires are doing. Before I show you the wires, take a quick look here at the potentiometer, and you can see that it's got 3 pins on the bottom. Those 3 pins correspond to these 3 rows on the breadboard. So on the left here we have this yellow jumper wire, which goes from the blue negative power rail into the first hole on this row. Then we skip a row, and then we have this jumper wire going from the red positive power rail into the first hole on this row. Then going down from there, we have these 2 jumper wires, which cross the center gap of the breadboard and cross over to the corresponding row on the opposite side of the breadboard. This green one on the left is in the same row as the yellow jumper wire up here. And then this other yellow jumper wire is in the row that we skipped. So we had this row, skipped a row, and then went to that one. So in this row that we skipped, it goes from the last hole on this side over to the first hole on this side. Then connecting right there to the yellow wire is this long white jumper wire, which goes across and connects to the left side of the resistor. The other end of the resistor connects to the same row as the positive lead on our LED. So as I've explained in previous labs, LEDs have a positive and a negative lead. The long lead is the positive lead, and the short lead is negative. So just place it in your circuit so that the positive lead is connected up here to the resistor. And then finally, the negative LED lead is connected in the same row as this long green jumper wire, which is connected to this green jumper wire, and that's connected to this yellow jumper wire, which connects to the blue negative power rail. So this long green jumper wire, the short green jumper wire, and then this yellow jumper wire, as well as the blue negative power rail, are all connected to the black negative battery wire. Now I need to place the potentiometer back into the breadboard, and when I do this, I just need to make sure that each of these 3 pins goes into a separate row corresponding to these jumper wires that we had connected to it. Now we need to connect our multimeter to the circuit so we can measure the LED voltage, and we're going to do that using an extra jumper wire and some alligator clip wires. So place the jumper wire in the same row as the negative LED lead, and then you can connect an alligator clip to that. Then take another alligator clip and connect it up here to the resistor. For the multimeter, we'll be measuring voltage, so let's check the ports. We want black in COM and red in V for volts, and then turn the dial to the 20 volt range. Now, the voltages we're measuring will be below the 2000 millivolt range, which is the next range down, but at that precision, the values fluctuate too much and make it difficult to see an exact value. So to compensate for that, we'll put it on the 20 volt range, and that kind of ignores some of those minor fluctuations. Anyway, I'm going to go ahead and connect this real quick. So I've got black here, and then the red one up here. So the negative probe is down here, connected to the negative LED lead, and then the positive is connected up here to the positive LED lead, or the same row at least. The last thing we need to do is add some black electrical tape to the breadboard underneath where the LED goes, and make a tube out of some black paper so we can isolate the LED from the ambient light and make it easier to see exactly when it turns on. So to do this, I'm going to remove the LED, and then I've cut off 2 pieces of black electrical tape. And I'm just going to place them down onto the breadboard right where the LED was. And then if I smooth them down onto the breadboard, you can kind of see the holes through the tape and sort of figure out where the LED was supposed to go. So I'm just going to poke it through the tape into the breadboard. So there, I got one side in, and there's the other side. Let's just make sure that it turns on. Alright, that works. And then for the tube of paper, you want to make something like this, so it's about the size of your eye, so you can look through it like that and isolate the LED. Alright, so this is about what you want for the tube of paper. You can use any sort of dark colored paper that you have on hand. If you have extra conductive paper from the earlier labs, you could use that, or construction paper or cardstock, whatever. It just needs to be dark, so when you look through it at the LED, all you see is the light from the LED and you don't see a bunch of reflections off the side of the paper. Now it's time to collect our data, and for this there are two parts. First, we need to measure the voltage necessary to turn on each LED, and then second, we'll use the spectroscope to measure the wavelength of light for each LED. Before we do that, make sure you have one of each colored LED, so there should be 4 colors. We should have red, yellow, green, and blue. And then there will also be a white LED from the inverse square law experiment, but we're not using that today. So make sure you just have the colored LEDs. And they will all look identical in the bag because they're all transparent, so you'll have to test them in the circuit to find out which colors are which. So the way I'm going to do this is first of all turn the LED all the way down. Use the potentiometer knob and turn down the brightness until the LED is off, and then look at the LED through the paper tube. So you press this up against your eye and look at it, so all you should see at the beginning is just darkness. And then turn it up very slowly until you see it just start to glow. If you go too high, then your eye will adjust to the bright light and you won't be able to see the dim light very well. Then once it's glowing dimly like that, turn it down slowly until it turns off. So at the point that it turns off, that's the voltage you want, and you can press hold on the multimeter and then save the value. When you do that, make sure to keep your fingers on the potentiometer knob, press hold, and then you can let go, because we found that the slight torque you apply with your fingers, if you let go, it changes the value just a little bit, and so you won't be saving the accurate value unless you keep your fingers on that knob. Now I'm going to start with the red LED, and I'm going to have to take my glasses off for this. So I'll just press my eye up against the tube, and then slowly turn the brightness up until I see it start to glow. There we go. Okay, so it's glowing now, and then I got to turn it back down until it just disappears, and right there is where I want. So I keep my fingers on the potentiometer knob, press hold on the multimeter, and then I can let go. And then I'll record the color, red, as well as the voltage, which in my case is 1.43 volts. I should also mention here that when you place the LEDs in the board, make sure that they're pointing straight up. If you have them at a slight angle, then the light won't be quite as bright and you might not get an accurate voltage. Now I'm going to swap out the red LED for the yellow LED, and when you place the next one in there, just make sure you get the polarity correct, otherwise it won't turn on. And then I'm going to do the same thing, so I'll press hold again to release it and go back to the live value, and then look through the tube at the LED, and turn up the brightness until it just barely glows. So right now it's glowing, and then I'll turn it back down until it just starts to disappear. Okay, right there it disappeared. No, okay, there. Now it disappeared. And I'll just press hold to save the value, and now I have 1.57 volts. So again, I'll record the color, yellow, and the voltage, 1.57 volts. Then you'll do the same thing with the other two LEDs, so again with the green and then with the blue, and each time record the color and the voltage from the multimeter. Now, one thing you may be wondering is how I filmed the LEDs while adjusting the brightness. And the truth is, I didn't. I filmed it after the fact. I used my smartphone, I filmed it through the tube, and then adjusted the brightness so that it would look the same as when I did it with my eye. But for you doing the experiment, don't do it that way. Just use your eye. Your eye is a much better light sensor than the camera, and so if you use your eye, you'll get a much more accurate voltage than if you try to do it with a camera. I only filmed it so you could see what it should look like when you do this. Now we need to measure the wavelength of light for each LED. And I know I said that we needed frequency, but frequency and wavelength are related, and we can find the frequency by dividing the speed of light c by the wavelength lambda. Just make sure when you do that, though, that you convert the wavelength into units of meters so that everything is in standard SI units. For this part, we don't need the multimeter, so I'm going to go ahead and remove all of that. And then we also don't need the tape that's on the breadboard, so if you want to, you can remove that as well. All we need now is the breadboard circuit and the spectroscope. And I'm going to show you how we can set these up hands-free so it's easier to do the experiment. To make this hands-free, we need to elevate the breadboard and the spectroscope, so we can line up the LED on the breadboard with the slit on the spectroscope, and then everything will be lined up vertically. We can look straight through the spectroscope, see the LED, and then read the wavelength on the wavelength scale. I'm going to do this with some objects from the lab kit. I just placed the jumper wire kit underneath the breadboard, and then the CD with the electrical tape roll underneath the spectroscope, and that brings them up to about the same height. Then we need to bend the LED at a 90-degree angle so that it points to the side directly into the slit of the spectroscope. One other thing that may be useful is placing something white behind the wavelength scale of the spectroscope. So this reflects light back onto the scale and makes it brighter and easier to read. So I'm just using the screen from the Lens Lab, but you can use whatever you like for this. Now to collect the data, just look through the spectroscope at the LED and then read the wavelength from the wavelength scale. So you want to line this up so the LED shines directly into the slit of the spectroscope. Then turn down the LED brightness with the potentiometer knob, and this will reduce the width of the smear of light and make it easier to get a single value. Alright, that looks pretty good now. I was able to reduce the width of the smear of light, and it looks like the central wavelength is around 470, maybe 475 nanometers. So then I'll record the color, blue, and the wavelength, 475 nanometers. And don't forget to convert the wavelength into units of meters so you can get the frequency in units of hertz. Now we'll just continue this process, so I'm going to swap out the blue one for the green one. And again, you'll want to bend it at 90 degrees so it points directly into the slit of the spectroscope. Then just line up the slit with the LED and adjust the brightness down until it reduces the width of the smear and read the wavelength value. Alright, that looks pretty good now, and it looks like the central wavelength is around 530, maybe 535 nanometers. So again, I'll record the color, green, and the wavelength in units of meters. And as before, we'll swap out the other two colors, so I'm going to put the yellow one in, and then we'll get the wavelength for that. Also, you should try to take a picture through your spectroscope. You'll need it for the lab report, and it also makes it a little bit easier to read the value. You can look at the picture, zoom in on it, do what you need to, and you don't have to worry about keeping things lined up while you're reading the value. And as usual, don't forget to unplug the battery when you're done with the circuit. And that's it. So make sure to read your instructions carefully. They will have more information than what is shared in the video, and good luck on your experiment.